Okay, so this is the theorem we mentioned last week. All right, and we have taken an example to illustrate that if the h function is a constant function over this closed interval, then this statement is true, because if h is a constant function, then we know it has a right limit at the 0 point. Okay, and also the difference is 0, because this is a constant and this is the same constant, so the difference is 0 divided by t. So you can think about that. So this is the zero function, and for any zero function, it is absolutely integrable. Okay, so the example we took in last week, just a special case of Dini's theorem. All right, and so Dini's theorem gives us a general condition for such a for this the Dirichlet integral to have limit equal to this value as alpha goes to infinity. Okay, so we are going to prove Dini's theorem now. Okay. All right, so we rewrite the Dirichlet integral in different form. Okay, so this integral is from 0 to delta 2 divided by pi. Well, you can, first of all, you can ignore the constant. So we just write here alpha t sine alpha t divided by t dt. So we just subtract a term and add the same term back. Okay, so, and we know this is a constant, so this is exactly the example we discussed before. Okay, so, and we know this term here by our assumption here. This term, okay, is absolutely integrable. So we can apply Riemann Lebesgue lemma here. Right? So as alpha goes to infinity, this integral goes to 0. Okay, so we can see that this term goes to 0 as alpha goes to infinity by Riemann Lebesgue lemma. Okay. The reason is that this function is absolutely integrable over U delta. Okay, so here, okay, well, it just okay. So now, all right. So the limit goes to infinity. Pi. So our original Dirichlet integral, okay, the limit is equal to the limit. All right, and okay, all right, and now we turn to the case we discussed in the last example. So this is equal to H0 plus. Okay, so the proof is easy, right? Proof is easy. This is the Dennis theorem. Okay, so now we go back to so we're going back to the convergence and the representation problem. Okay. All right, so we have that the GT X has been defined okay, and then, all right, so this is just like the h of t, right? The h function, and then we evaluate the right limit. So the right limit is here. Okay. When the limit exists. Okay. So, of course, it may not be true that the limit exists, but just suppose it exists, then we know that this is just this limit. And if f is continuous at x, then so if f is continuous, then G0 plus exists, and is equal to f of x. Okay. Yeah. Okay. So, because if f is continuous, then f has so f has a right limit at x, as also has left limit at x. So that when x go to 0, this is go to f of x, and this one is also go to f of x. And so divided by 2 is go to f of x. Okay, so in many situations that you can see that f is continuous as x. So in this case, all right, we know this result. Okay. But we want to find some conditions that that the premises of Dini's theorems are true. Okay, so we want to know conditions, because here H is just that in our convergence and representation problems, we have G functions here. Okay, so we want to know conditions on F such that this G function has right limit at 0, and this G function divided subtract the right limit at 0 divided by t is absolutely integrable. Okay, so we want to know, and so we make a remark. Okay, if the periodic function f has left hand limit f x minus and right hand limit f x plus, it's a point x in R, i.e. We know x minus its limit. We can use delta goes to 0, x minus delta. Okay. All right. So the left hand limits is that for all, because when x minus delta is positive but goes to 0, this is just all the points at the left hand side of x. Okay, and as delta goes to 0, then x minus delta will approach x from the left hand side, and the function value has limit. Suppose we have that. And this is the right-hand limit. This is because x plus delta is a point at the right-hand side of x. So as delta goes to 0, then this means that delta is positive, but going to 0. Okay. Then so that f of x, so x plus delta will approach x from the right-hand side. Okay. All right, so suppose the periodic function has left-hand limit and the right-hand limit at a point x. Okay. Then g function, g plus x. Okay. By definition, t. Okay. Oh, I'm sorry, it's not x. I have made a correction t. Okay, sorry about that. So t so this is let me see. So this is g of t x, and so this is limit. Okay. All right. So you can think about that. The t is just a delta here. Okay. So that is 1/2, and so this is right hand limit, and here this is the left hand limit. Okay. Okay. So under this condition, we know the g function has right hand limit at 0. Okay. So or x. Okay. Because x here is just a parameter, right? It's a parameter. So now we find a good condition for this exist. And so now we want to find conditions such that gt x minus g 0 plus x divided by t is absolutely continuous. Okay. All right. And the condition we find is here: if f has left hand derivative and right hand derivative at the point x. All right, so let's review what do we mean that a function has left hand derivative. Oh, or have right hand derivative at the point. Well, so it means that the two limit. So when we compute the two limit, is f(x) minus t minus f(x) minus divided by minus t, and for limit t equals to 0. Okay. So we just require, so from this formula you can see that first of all, f should has left hand limit at point x first. Okay? It's the left hand limit. So the difference is that this is a point, right? This is a point to the left of x. Okay, so it's to the left of x, and this one is the left hand limit. So the difference. Okay, and the minus t is because the difference from x minus t minus x. So this is minus t. Okay. And this limit we call L, and the limit we use right hand limit. So this is t, it's R. Okay. Okay. So furthermore means that the periodic function has left hand limit and right hand limit already, and then we also assume f has left hand derivative and right hand derivative at the same point x. Okay, so that means that the two limiter, these two limiter, the two limiter exist. Okay, all right. Then for any epsilon greater than 0, there exists a delta greater than 0 such that, okay, so from the definition of limiter, we know this means that f x minus t minus f of x minus divided by minus t minus L. Okay, so when we look at the difference between this ratio and the limiting value L, if you want the difference is a small number, less than delta, right? Also, divided by t, the difference minus the limiting value, okay, for all t in for all t between, okay. So if we want the other, okay, the difference is less than epsilon, you can see epsilon is very small, then you can always find a delta such that when t is between 0 and the delta, okay, because t is going 0, but never equal to 0, okay, t can be very, very small, but never equal to 0. So this is the meaning of this notation. Okay, so you can find delta, okay, have this property. All right, so this is the meaning of a limiter. If you look back to your calculus textbook, okay, you know that. Okay, so in particular, there exists, okay, a delta greater than pi. No, a delta. So a positive delta less than pi, such that from here we know fx minus t minus fx minus divided by minus t. All right, so the difference, okay, is less than L plus epsilon. Okay. By the triangular inequality, okay? If you wonder anything, well, you can okay, yeah, right. So you have two the addition of two numbers. So by triangular inequality, so you have minus t plus okay, but the absolute value of difference is less than delta, so this is equal to epsilon. And similarly, x plus t minus f of x plus divided by t is less than equal to r plus epsilon. Okay. Okay. Okay, and so now the G, T, X. So now for T, it's in between delta. Okay, G0 plus divided by T, and we take the absolute value. And you can see that the G function, so we have 1/2 here. So f of x plus t minus f of x probably I write it down. Okay, so okay, this is x plus t, x minus t. Okay, divided by t. Okay, and so so we do here, and okay, and when we take the absolute value here, and applying the inequality, so we have epsilon. All right, so this ratio, the absolute value of this ratio, is bounded, okay, over this interval. Okay, so that the integral of okay, it's finite, all right, and so gt x minus g0 x divided by t x absolutely integrable over 0 and delta. And well, even though so the value of g function of the difference divided by t at the t equal to 0 can be defined arbitrarily. Okay, so it's not essential, because in terms of the integral, okay, the two boundary, because our integrator is dt, is the infinitesimal t. So the two endpoints is not important. Okay, so now, so you can see that the premises stated in Dini's theorem, this one and this one, all right, can be fulfilled for the G function. The G function, when what? When the periodic function f has left-hand limit and a right-hand limit at the point x, and has left-hand derivative and the right-hand derivative at the same point x. Okay, so these conditions are not very restrictive, right? Actually, in practical situation, the periodic signal we considered in engineering world, or in most of the mathematical world, that we do have this condition here. Okay, all right. So we'll consider a broad class, and I'll state that a function, okay, f defined, all right, on a finite, all right, defined on a finite closed interval AB is called piecewise continuous. Okay, if there exists a finite number of points okay, A, the boundary point is defined to be x0, x1, x2, and the xn minus 1, xn defined to be B, right? So suppose that in this finite closed interval, we find a finite number of points. And the first point, x0, is just the left boundary A. And the last point, xn, is the right boundary B. And we have intermediate points here. Okay, well, we can find the finite number of points such that f is continuous. All right, so that f is continuous on each open interval for all I from 1 to n. Right, and the left hand and the right hand limit. Okay, so at the point, because we have left boundary, so we only have right hand limit at the x0, but we have left hand limit and the right hand limit at the x1, etc. And we have left hand limit and right hand limit at x sub n minus 1. And the last for xn, because xn is equal to b, and b is the rightmost endpoint, so it has only left hand limit. Okay, so we have those left hand and right hand limits exist. So the idea is here. So this is A, this is B. So A is equal to x0, x1, x2, x3, and x4. Suppose that we have that. And okay. All right. So we may have that. Okay. maybe the endpoint here. Okay. So you can see that in each subinterval, subopen interval, the function is continuous. Okay, and we can see that at x sub 0 we have right-hand limit, right? Because that the value goes to here, even though the right-hand limit is not equal to the function value at x0, because f of x0 is this point. Okay. So the function is not continuous at x0. Okay? It is not continuous at x0. And similarly, the function is not continuous at the x1. Okay? And at x1, the function has right-hand limit, and as well as has left-hand limit as well as right-hand limit. And its right-hand limit is just equal to its function value. Okay? Right. All right, so this is a typical function stated here. So such a function is called piecewise continuous, because it piece by piece is a continuous function. Okay, but we do require that at such finite points, which are used to divide the interval into subintervals, at those points, left-hand limit and right-hand limit exist. Okay, these are additional requirements in the definition of piecewise continuous function. Okay, so any questions about such a function? So now it is clear that a piecewise continuous function on AB is absolutely integrable. Okay, over AB IE is finite. Okay. Okay. The reason is that this integral is equal to the sum of integral of each piece in the corresponding subintervals. Okay, and you may think about that. In here, the integral. So the integral, for example, the integral from x0 to x1. Okay. Now we can define a continuous function. Okay. So we define a continuous function called f1. Okay, called f1. And f1 is continuous on the cross interval. Okay, the cross interval. Because we define the f1 of x0 is equal to the left limit, the right limit of the f of x at x0. Okay, and you can see that x0, x1, f1 t. Okay, so the integral over this subinterval of the original function, right? Here, the absolute value of the original function is equal to the integral over the same subinterval of a function f1. Okay, and this f1 is continuous function on a closed interval. It is continuous at the two boundary points. In calculus, we know such an interval exists. Okay, exists because that it has the maximum value and minimum value. Okay, so so the original function is absolutely integrable over each subinterval, and the original integral is just a sum of the absolute value of f function over all the subintervals. Okay. Okay. So it can be seen that a piecewise continuous function on AB is absolutely integrable. Of course. Okay. So it's a it's a nice property to have. All right, and so we can state our main result of Fourier analysis of periodic signals. So this is the representation theorem. All right, so representation by a trigonometric Fourier series. All right, trigonometric Fourier series. Okay. So assume a periodic function f with a period 2 pi have the following properties. One, it is piecewise continuous. Okay. So it's piecewise continuous on one period. Okay. Second, it has left-hand derivative and right-hand derivative. Okay. At each point, of minus pi to pi, right? Okay, so it is piecewise continuous on this interval. So now, which means that at every point, it has left-hand limit and the right-hand limit. Okay? And it is absolutely continuous. Okay. And because it is absolutely continuous, so it has a corresponding trigonometric Fourier series, right, generated by f. So we can construct that. Okay, we can construct that. All right, so then the trigonometric Fourier series A0 plus summation m minus n equal to 1 to infinity an cosine nx plus bn sine nx generated by f, right? Generated by f. So, right? So we can generate such a trigonometric Fourier series is because f is absolutely integrable over one period. Okay, as we discussed before. Okay, so we can compute the coefficients a0, an, bn there. Okay, so now then this Fourier series converge. All right, so converge to f of x. All right, so it will converge to f of x, except, okay, except at points, okay, f where f is discontinuous. Okay, where f is discontinuous. Because f is piecewise continuous, so that it is continuous except a finite many points in one period. I mean in one period. Okay, in the whole real line, if it has one discontinuity, then it has infinitely many discontinuities because it will repeat again, right? So, okay, this trigonometric Fourier series generated by f will converge to f of x. So we solve the representation theorem, except at point x where f is discontinuous. And there, right? So at those points where f is continuous, where the sum of the series, okay, is the average of the left-hand limit and right-hand limit. Okay. Okay, so the theorem here gives us a positive answer about our questions. Okay, our two problems, the convergence problem and the representation problem. Okay, so it's actually it answers both problems simultaneously, and the periodic function given here those periodic functions having these two properties. First of all, it is piecewise continuous. all right, on one period. And of course, it's piecewise continuous at every finite interval. And it has left-hand derivative and right-hand derivative at every point, all right, of this interval. Okay. Right. So these two properties is not restrictive. Okay, it's still very general. And so under these two conditions, then the trigonometric Fourier series generated by F, okay, this series converge at every point. Okay, so the theorem answer the convergence problem says that this trigonometric Fourier series converges at every point. Okay, and it is equal to the original function of x at those point x such that f is continuous. But for those points such that f of x is discontinuous, then we know that the sum of this Fourier series is just the average of the left hand and the right hand limit. Yeah. Okay. Any questions? Okay. Okay, so I think the proof is straightforward. Once we understand the previous discussion. So proof. Right, so f is piecewise continuous. Okay, on one period from minus pi to pi implies, first of all, f is absolutely integrable over minus pi to pi. Second, f and the right hand limit exists for all in. Okay. Yep. Okay. All right, and this one, the first condition implies that f generates a trigonometric Fourier series. Okay, we call A0 plus so, all right, so f is piecewise continuous. We have this one. Okay, and also, furthermore, okay, oh, by the way, so the second point implies that G0 plus x okay exists okay for all okay, so we have okay, so this condition implies that two things here. Okay. Also, f has left hand and right hand derivatives. Okay. Implies that we can apply Dini's theorem to okay, as discussed in the previous remark. Okay, so the conclusion is that the limit of the partial sum sequence Xn of x of the trigonometric Fourier series. Okay, Fourier series exists for all x in this cross interval. And the important parts here, okay, the limit n goes to infinity xn x, okay, is the limit as we computed before, because that this limit, okay, n plus 1/2 t divided by t and the dt here. Okay, so this one. And this by applying Dini's theorem, okay, the partial sum limit will goes to this number for each x. Okay, and this is just equal to divided by 2. Okay. All right, and this is what we have here. So when f is continuous as x, then of course this sum, this average is just equal to f of x. Okay, f of x. Any questions? Okay, so I think so such a representance theorem is broad enough for practical applications. Okay, right. So okay. So this is today's lecture. So I'll see you on Thursday.